Okay, shall we start the morning session of second day? And the first speaker is Paolo Pani from Roma. He's going to tell us about the new physics on the horizon. Paolo, please start.
Okay, thank you very much, and good morning, good evening, everyone. Thanks for this kind of invitation. I would have loved to visit Russia for the first time. Hopefully, it will be possible in the near future. Okay, so I would like to present some recent developments and results about testing the nature of compact objects, and in particular, new physics at the horizon scale. And I will discuss several scenarios and tests, but by the end of my talk, hopefully it will be clear what kind of phenomenology we expect from objects that look like something shown here in this embedding diagram as compared to the curve case here. And I will explain better what these diagrams are. Okay, so for those of you who are in the field for some time now, maybe you remember that black holes were not so fashionable just a few years ago, but now they are everywhere. We have evidence for black holes across huge mass range, both stellar masses, as in LIGO Virgo, or supermassive ones at the center of galaxies, or even very big monsters in other galaxies. And this was worth 2 Nobel Prizes recently. So an important question is, why should we test the black hole picture, since we have so much evidence nowadays for black holes in the universe? And I think there are still very important motivations to do so, and let me just give you 3. The first one is that there might be other compact objects other than black holes and neutron stars in the universe. And in this respect, there are some hints maybe for something different from the standard astrophysical paradigm. For example, in LIGO Virgo data, there are some events populating the mass gap that should not be populated from standard formation scenario in astrophysics, or also the problem of supermassive black hole C. So we don't know how to explain supermassive black holes at high redshift. And in general, since we know that most likely there is a dominant dark matter component in the universe, this dark matter component might form self-gravitating objects like boson stars or axion stars that we might also look into data, essentially. The second motivation is more fundamental because we might want to test some quantum gravity paradigm that predicts new physics at the horizon scale. And they try to address the information loss paradox of the standard black hole evaporation, the singularities inside black holes, and problems in general associated with the interior of black holes. There are different paradigms in this respect. Some invoke, for example, firewalls or very strong non-local effects near the horizon. Others require the existence of regular, so singularity-free horizonless compact objects, like in the fuzzballs proposal. This might be a bit speculative, but I would like to stress that this is the right time to ask these questions, because if we don't do it now, probably we'll never do it. We are currently in a situation in which we have plenty of observations, and in the future, things will improve a little, but basically the kind of phenomenology that we can probe is already at hand. And finally, we want to quantify in general the black hole, let's say, of different sources across mass ranges, different mass ranges, because, for example, we want to do Bayesian model selection between the black hole hypothesis and something else. So we need models and predictions. It goes without saying that observation of anything that will not be a black hole or neutron stars will imply either new physics or new matter field. So it would be, of course, a major discovery. In this context, I will talk about exotic compact objects. So for me, exotic compact object means objects that are very compact and they are nor black holes nor neutron stars. They come in very different flavors. I think that they can roughly divide it in, say, solutions to general activity with exotic matter, so not necessarily beyond GR physics, or solution to modify gravity. And there are many examples. Sometimes the 2 categories actually overlap, so it's not clear whether one if there is a sharp distinction. For most of my talk, I'll try to be as agnostic as possible, so do not focus too much on particular models and try to discuss the phenomenology in general. Precisely to do that, so it's important to understand the parameter space that one would like to probe, so sort of quantify the shades of darkness. And if one looks at one source, say in the sky, a black hole candidate, I think there are at least two-dimensional parameter space to probe. One is the compactness, so essentially how compact the object is. This can parameterize by a parameter epsilon that tells you in units, say, of the black hole horizon, where is the effective radius of your object. And the other is the reflectivity. So how much energy is absorbed by this object in its interior. A black hole, of course, sits here, 0 reflectivity and 0 epsilon, but there are different corners in this parameter space. So small compactness, no absorption, typical of boson stars, small compactness, large absorption, and I mean, all possibilities. And of course, the closer we are to the black hole limit in these two dimensions, the more difficult it will be to tell alternatives apart. In this diagram, there are two important regions. One is when epsilon is over the unity, because objects with smaller epsilon have a light ring, and this has important implications for the phenomenology. And the other is if one has in mind some quantum gravity proposal, typically the horizon is just, say, Planck length away from the radius is just Planck length away from the horizon in a sort of effective way, and therefore this epsilon is tiny, it's 10 to minus 40. And in principle, one wants to probe this huge parameter space and also this dimension here. Yeah, and this is essentially the goal for present and future observations. In GR, there is an important theorem due to Buchdhal showing that under certain hypotheses, this epsilon parameter cannot be arbitrarily small. So there is no continuous limit to the black hole case. Epsilon has to be bigger than this number. Of course, this is a theorem. There are many hypotheses, and by relaxing each one of them, one can try to break the Buchdhal limit and produce much more compact objects. And of course, one of the hypotheses is classical generativity. Another one is isotropy, and this is very important because most models of exotic compact objects have one way or the other strong anisotropies. So let me briefly give you 3 examples. I don't want to enter in any detail here. If you want, we can discuss them later. First one is boson stars. These are probably the most studied examples because they are more well-motivated and consistent model. It's just a complex scalar field or a vector field minimally coupled to gravity with some self-interactions. Depending on the self-interactions, these objects can be very compact and can have a maximum mass that essentially is set by the parameters of the potential. And these solutions do not require any beyond GR effect. Another examples are anisotropic stars. So instead of having just a perfect fluid, one can develop, even within GR, models that have anisotropies in some directions. And these models can be much more compact than a standard neutron star. So here I'm showing the mass radius diagram. This is for a neutron star. And by increasing, say, an anisotropic parameter, one can have models that are stable, have a Folon sphere. They can even beat the Buchdhal limit and be as compact as black holes. And it's important to stress that anisotropies here are really key to build these models. And finally, going, say, just one example, which I think is very interesting and motivated for beyond GR effect, are fuzzballs. So fuzzballs is a paradigm, essentially, where the classical black hole is replaced by an ensemble of regular horizonless microstates, so that instead of having a singularity here, they have a regular cap. And the idea is that a black hole is seen as a sort of average over all these huge number of microstates that can also account for, in principle, for the black hole entropy. This model has several interesting properties. One is that it's well motivated. It arises from a consistent theory, string theory, or low energy supergravity approximations. And most importantly, the mass of the solution in this model is a free parameter. in boson star is not. Once you fix the scalar potential, the max is fixed, the maximum mass is fixed. Here is really a free parameter like in the black hole case. So you can explain in principle all black holes in the universe with this paradigm. The cons are that, well, solutions are very complicated. Most of them are built only for extremal or almost extremal charged black holes. There has been recently some non-SUSY extension, and there is a lot of discussion going on. This week, for example, there is an interesting workshop on black hole microstructure in Paris, by the way. Of course, it's online. And for any detail on the phenomenology, I can suggest this review by Daniel Meyerson that I think is very well done. Okay, so for because time is limited, I would like to focus only on gravitational wave-based tests of exotic compact objects. So I won't touch at all electromagnetic tests, even though they are interesting. And the picture I would like you to have in mind is schematically described here. So this is the typical coalescence of a binary system in which differences between the case where the two objects are black holes or something else show up in the inspiral, in the merger, or in the ringdown, with different effects. And my goal now for the rest of my talk would be to go through many of these effects and try to explain them a little. So let me start with the very last part, the post-merger phase that is dominated by the ring down of the REM. So the picture is that the two objects merge, they form a perturbed object that vibrates and has a peculiar signal that is called ring down. So in the prompt ring down, essentially right after the merger or sometime after the merger, the signal can be decomposed in a superposition of quasi-normal modes, so complex frequencies. And well, these frequencies and damping times have been started to be measured by LEGO and Virgo, but in the future, we will detect hundreds or thousands of events for which black hole spectroscopy can be done. So for which one or more quasi-normal modes can be detected. And in general, if the final object is not a curved black hole or is not a black hole at all, there will be some signature. One, of course, is that the spectrum that for a curved black hole depends only on mass and spin would be different. Another one is that there might be other modes, like due to extra polarization, for example, scalar modes or fluid modes that might be excited. An important problem here is the amplitude, the excitation factors for these extra modes, depending on the model, of course. And then there are other interesting effects like isospectrality breaking that occurs essentially for any model, almost any model beyond GR or beyond Kerr. An important point is that studying the ring down beyond a case-by-case analysis is tough. Recently, what we have been doing with PhD student Elisa Maggio in Rome and other collaborators was to try to develop a sort of model-independent framework to study the ring down of exotic compact objects. And the idea here is to use the black hole paradigm. So in the black hole membrane paradigm, in the black hole membrane paradigm, the horizon is replaced by a fictitious fluid, so a membrane made of a fictitious viscous fluid, and all properties of the horizon are mapped to physical properties of this fake membrane. For example, the quasi-normal modes can be explained in terms of a shear viscosity for this membrane that has this peculiar value in order to match the black hole case. What we did in this paper was to extend this to a more generic model in which instead of having the horizon, you can have a radius at some position that is a free parameter, and the viscosity is not fixed by this value, is a free parameter as well. The reflectivity coefficient that was mentioned before is related with the viscosity roughly in this way, which means that in the black hole case, of course, the reflectivity is zero. And then you can ask, what is the ring down in this system? You can explore a two-dimensional parameter space, as I was mentioning before. These are the relative difference compared to the black hole case. And already the very first gravitational wave event put some constraint on these numbers, real and imaginary part. And this gray area is the only one that is not excluded by GW1500914. Interesting enough, if one increases the signal to noise ratio, as will be done in the future by a factor of 10 roughly, all this region will go away. So in principle, one can constrain the entirety of this diagram. An important point is that you see this diagram stops at epsilon 0.01, and the reason is that for smaller epsilon, the prompt ring down is identical to that of a black hole, and the reason is that it's essentially related to the photon sphere barrier that is present in any ultra-compact object. However, in this case, what will happen is that there is a signal, a post-merger signal that appears, some feature after the prompt ring down. So the initial prompt ring down is identical to black holes, but then because of mode that can be trapped within the potential barrier of the object and its interior, there are what has been called gravitational wave echoes appearing at late time. An important point I want to stress is that this effect inevitably should occur anytime you don't have a classical horizon, because essentially, by definition, only classical horizons absorbs everything. But if you have, say, some matter field very close to the horizon, or some fuzziness of your space-time, or quantum emission from the horizon, anyway, you will have some reflectivity. So something will go back from the horizon. Of course, one can ask what is the reflectivity coefficient in this case, and it might be model dependent and very small, but it's an interesting question to see to which level we can constrain these effects. There's been a lot of progress in trying to model echo waveforms and perform searches, and this is a nice review that I can suggest. Very briefly, I don't want to spend too much time on this, but there has been contrasting results on the presence of echoes in current data. The current situation is that different groups do not agree essentially on the level of statistical evidence for this, but the LIGO-Virgo collaboration is searching for echoes and has developed pipelines for this, which I think is very interesting. And they claim that there is no statistical evidence up to essentially the data that has been released last year. I also want to stress that the echo waveform is very complicated, and here is just a slideshow for different spin of the remnant, different reflectivity. And as you can see here, there are two colors because there might be two polarizations. So a real waveform should include mixing of polarization, spin effects, frequency modulation. So the signal is very complex. And this is not what has been used so far in searches. So I think an important point would be to extend this in the future with more realistic signals. And still, this complexity is for a sort of toy model in which one sort of parameterizes the reflectivity coefficient, and there are some simplification. The situation in reality is actually much more complicated, and very recently with Taishi Keda and string theories from Toro Vergata in Rome, we studied the problem of ring down for a real solution of exotic compact object given by one of these black hole microstates that exist in n equal to supergravity for a simplified problem. So this is a test scalar field propagating on this geometry. Now, this geometry is very complicated, and in fact, it can be arbitrarily deformed relative to the black hole case, and I will discuss this in a moment. But it's interesting that one can study how the scalar field propagates here and recover the phenomenology I was mentioning before. In particular, here I'm showing that some time snapshot of the scalar field. It's initially spherical. In the black hole case, first row, and you see that it just remains spherical and dies off as in the standard picture. Or in other cases for these fuzzball solutions, in particular this axisymmetric case and this case that breaks even axial symmetry, and you see two features. The first one is that they are deformed, both so the spherical shape is deformed, but also that also at very late time, you still have some ring down. And maybe this is more evident. Let me just play this movie for you. Say this one here. What you will see now is how the one of these microstate geometries ring down, And pay attention, please, to this time that goes, and you see that even when this is a unit of the black hole, of the object mass, and you see that even at very late time, there is still some pattern, and the deformation, the shape, the fact that the object is not spherical is clear from this ring down. The signal that I was playing before is more clear here. And interesting, you see a few features. The first one is that the initial ring down, so this is for the black hole case, and this is for the fuzzball case. So first you see that there is mode mixing. This is L equal 2 and this is L equal 0. So even if the perturbation is initial spherical, you can have different modes excited. But not only that, initially the ring down is very similar to the black hole case, and at later times you see some echo pattern and a long tail due to the long-lived modes of the fuzzball. All of this is much less clean than in toy models that I showed before. And the reason is that these are complicated solutions when there is no symmetry. So this is to show that in reality, the situation can be much more complicated. I mean, in reality, meaning for consistent models rather than for toy models. But it's interesting that all the phenomenology is sort of recovered also in this case. And as a bonus, what the study showed is that microstates are dynamically stable, at least for a test scalar field, which was not at least guaranteed, was expected, but not guaranteed for this case. In particular, these solutions do not have ergo regions, so they are not unstable for the ergo region instability, even if they are spinning. Okay, in the rest, I think I have less than 10 minutes. I would like to discuss not the ring down, but the first part of the gravitational signal, so the inspiral, and what we can learn from it. We can learn a lot, in fact, for various reasons. So the first one is that the phase of a gravitational wave in the inspiral in the post-Newtonian approximation contains information about the multiple moments of the objects. And we all know that the multiple moments of a Kerr black hole satisfy this elegant relation that depends only on the mass and the spin, both the mass and the spin multiple moments. For exotic compact objects, this is not true anymore. There can be deformation on the mass and the spin relative to the Kerr case, and objects can be deformed, in principle arbitrarily deformed, and here I'm showing the bending diagrams that Guillaume Raposo for this project produced. But not only that, it's possible to show that these corrections in the black hole limits on when epsilon goes to 0 have to be small, otherwise, unless essentially the curvature of the space-time diverges, and they have to satisfy the scaling with this logarithmic behavior of epsilon, which is interesting because this is the same echo delay time shown before, this log of epsilon correction. It's important because it gives you a handle to test very small value of epsilon, of course, because if it scales linearly, this correction will be tiny when epsilon is very small. All these solutions can be constructed. They are very complicated, but they can be constructed perturbatively in these multiple moments, and we have some examples on our webpage. It's also interesting that for fuzzball that was mentioned before, but also for other solutions, for example, boson stars, not only there can be deformation of the Kerr multiple moments, but there can be moments that are 0 in Kerr just because of symmetries that are broken for other solutions. For example, the Kerr solution is equatorial symmetric. If you have non-equatorial symmetry, you can have current quadruple moments or mass octuple moments that are 0 for Kerr. Or in general, if the solution is not axis symmetric like this one here, you can have a quadruple moment tensor that is just one number for Kerr. And this diagram, what it's showing is the shape is the mass moments, and the color scheme is the current moment. So to try to show both moments in a single plot, you see that the object is not axisymmetric, and also its current moments are more complicated. And there has been a lot of interesting results recently on this front for fuzzballs, essentially. And one important take-home message is that current models of waveform models do not include all these effects, and they should be extended beyond Kerr symmetry to be useful for phenomenology. Another effect that occurs in the inspiral, actually two effects that are sort of related, are tidal heating, so the absorption of the energy at the horizon, if there is an horizon, or the tidal deformability, so the fact that for black holes, the multiple moments induced by tidal fields are zero, while for an exotic compact object they are not. So in this sense, an exotic compact object behaves as a big and compact neutron star, so it can be tidally deformed, and this effect plays a role in the waveform. Interesting enough, again, the tidal log number, so the quantity that enters in the waveform, scales logarithmically with epsilon in many models, which again means that even when epsilon is very small, this lambda is sufficiently different from zero that can in principle be tell apart from a black hole for which lambda is exactly zero. I think I would skip this because it's not super relevant. My next to last slide is about sort of future constraints. And an important point is that in the future with the mission LISA, the space mission LISA, we are gonna see different sources, in particular extreme mass ratio spiral. So a small stellar-like object orbiting the supermassive ones. These are really unique probes for test of the nature of compact objects because they probe both the multipolar structure and the dynamics of your theory. And they made a lot of cycles in band before plunging. And these allow to put incredible constraints on many parameters. For example, the spin-induced quadrupole moment I was mentioning before can be measured within 1 part in 10⁴. The reflectivity can be measured in principle at this level, which is pretty impressive. The tidal log number can be measured at this level, which is a few orders of magnitude better than what LIGO and Virgo can do now for neutron stars. And in general, almost all tests of fundamental physics, GR, and the nature of black holes will improve by orders of magnitude with this. There are also many challenges because modeling of MRIs is difficult, parameter estimation is difficult as well, and we don't know the rates, so we don't know how many MRIs LISA is gonna see, but this is very promising. And let me just close with one example of a very recent paper that will appear probably next week. In this paper with Elisa Maggio and Martins van der Ment, we are studying the differences between an object that is Kerr or an object that has some reflectivity. And what I'm showing here is the mismatch between the two waveforms computed in LISA for a given amount of observation time. And this line here roughly corresponds to when the two waveforms are indistinguishable. So if you are below this line, there is no hope to distinguish them. But you see that for many cases, also when the reflectivity is super tiny at the level of 10⁻⁸, after 1 year of data, you break this limit. This, of course, is not showing that you can measure such as small values, but there is hope after doing a proper parameter estimation that LISA will be able to reach this value, which is really impressive compared to current constraint that put an upper bound of reflectivity of order essentially unit. So my conclusions, we are leaving the black hole era. There are really plenty of new observations. I just focus on a few today, and there is plenty of opportunity for discovering new physics. There has been a dramatic improvement on the understanding of exotic compact objects, both on the theory side, on the phenomenological side, and on the observation side. And these models are now taken much more seriously, including within the experimental community. Any signature of beyond Kerrness will shake physics on its ground and will be a major discovery. And already current observations put strong constraints both on the existence of light rings and the compactness of the object and on the reflectivity. In the future, we will expect much better constraints. And I think it's interesting in this respect that many of these observables scales logarithmically with the compactness of the object in a sense that shows us that horizons might be very spatial. And this is maybe our best hope to try to probe quantum gravity effect near the horizon. Okay, I think I will conclude here, and yeah, I will take your questions, and thanks for the attention.
Thank you, Paolo. It's just 30 minutes. Great.
No, great.
Okay, so question and comment, please. You can directly ask or raise your hand on the some list. Oh, Efrain, please.
Can I ask a question? So, Paolo, can you go back to the slide where you show the no-hair theorem and multiple moments there? So I was wondering about this. The last part of it, you say in the black hole limit, there is. Can you explain a bit what is this hair conditioner theorem? And what assumptions are there?
Yeah, I was a bit fast here, sorry. So what we did here was to build solutions within GR, so assuming GR in the exterior, that are arbitrarily deformed. So essentially these solutions here that they can have a spin, a generic quadruple moment, or combination of them with different moments. So these are perturbative solutions, but analytical one within GR. And then essentially ask the question, how small this deformation from the Kerr multiple moment should be in order for the curvature of these solutions at the effective radius in order for this curvature not to diverge in the epsilon going to zero limit. So the black hole limit here means that epsilon is very small, and unless they go to zero sufficiently fast, the curvature blows up. And they can go to zero in two different ways. The first one is that if they are spin induced, so if these corrections are proportional to some power of the spin, they have to go to zero logarithmically with epsilon or faster, otherwise the curvature diverges. Or if they are not spin induced, so if really they are intrinsic moments, they can go to zero linearly or faster in order for the curvature not to blow up. And the assumption behind this is that the space-time outside the radius is sufficiently well described by GR, and that you want the curvature near the surface to be not small, but say not parametrically larger than Kerr. Of course, if you are fine with having, say, Planckian curvature at the horizon, even for say a supermassive object, then you don't need to require this correction here. But if you want the curvature to be of the order of that of a black hole, then these moments have to be, this correction to the moment has to be small. So we call it hair conditioner, because it means that they can have hair, but not arbitrarily large in this hypothesis.
But do you assume that outside is vacuum GR?
Yes, outside is vacuum GR.
Oh,
yes.
Okay, thanks.
Oh, next, Valerie, please.
Yeah, concerning your echo, is there a gap between the black hole with its horizon and horizonless objects, in the sense that, you know, the energy emitted is grossly different? I mean, is there a gap between the energies emitted by the two objects, the black hole and horizonless object, or you can smoothly tune parameters of gap of any object in such a way that the energy emitted goes to zero? There is the difference between the black hole and horizonless object disappears smoothly.
Yeah, so in general, yes, there is always some parameters that smoothly connect, say, the exotic object to the black hole one. In toy models, this is essentially built, this is by construction. For example, this reflectivity R is the parameter that when it's zero, recovers the black hole case, and it means, for example, that these echoes, the amplitude becomes smaller and smaller as R goes to 0, and you really recover the black hole case, also in terms of energy emitted and any observable. And this is for the toy model. For, say, specific model like
excuse me, but
yeah.
Can R be arbitrarily small in realistic models, or not very realistic, but self-consistent models?
Right, being this a toy model, this is essentially, in this case, it's really like a free parameter. So there is no way to say one or the other. Precisely to answer the question, in a consistent model that I will take, for example, this one here. So this is a consistent solution to supergravity theory. Here, these solutions, for example, are multi-center solution. It means that they have different charges in space. It can be an arbitrary number of charges. And when these charges collapse to a single point, you recover the black hole limit. So for example, here we are considering 3 charges solutions. When these 3 charges collapse to a single point in space, you recover the black hole solution.
But
so here,
the horizon in this case,
this solution with more than one center do not have an horizon. And when
the centers collapse, do you?
They do, yes, they do.
So basically, you say that okay.
So here in this case, the parameter that continuously interpolates between this solution and black hole is the distance of these centers. When they collapse, you recover the black hole case, and all the phenomenology scales with this parameter. And yes, it can be arbitrarily small. Actually, in that case, typically, I mean, it's not guaranteed, but one would expect these centers to be the distance to the order of the Planck scale, because this is a quantum gravity model.
No, if not talking about quantum gravity, if talking about more, understandable things like, cue balls or Bose stars or anything like that, which you really have a handle on. Do you have a smooth, limit?
No, in that case, no. Yeah, I would say another very consistent model is this one here, Boson stars. In this case, you don't, because of what I was mentioning before, that depending on the parameters of your potential, you have always a maximum mass and also a maximum compactness. I think maybe from this plot is clear. This is the compactness, and this is, the parameter, or some parameter of the boson star. A black hole, a non-spinning black hole in this case, will have compactness 0.5. And as you can see, no models can reach there. So these boson stars can break, in principle, actually, the Buchdhal limit, but there is still a sort of gap to the black hole case. So there is no way you can make it arbitrarily close to the black hole.
Okay, thanks.
Alex?
Hi, Paolo.
Hi.
Very nice talk. So you have exactly this slide. And I'm a bit wondering, so do you know a simple reason why this complex scalar field there does not behave as a perfect fluid? Because in some sense, if it does not, then it's also like similar to this anisotropic fluids, I think.
In fact, it's precisely because of that. If you take the stress energy tensor for this scalar field and interpret it as the stress energy tensor of a fluid, you will see that it's anisotropic. Sorry. So this solution breaks Buchdhal theorem precisely because of that. Because of that. They are anisotropic. Yes. So is I would say yes, a consistent model of an anisotropic fluid. Of course, it's not really a fluid because it's a scalar field, but yeah, it's anisotropic.
Perfect. Thanks a lot. Very interesting talk. Thanks.
Okay, so thank you, Paolo. Yes, it's time to finish. So
thank you.